Good afternoon, everybody. Welcome to this Spotlight Talk session, the first one of the season. And my name is Boelo Schuur. I'm the Scientific Vice President of the European Federation of Chemical Engineering. I have recently joined the board of the EFCE, and it is an honor for me to serve the chemical engineering community in this role. As the scientific vice president, it's my role to support the scientific groups. These are the working parties and the sections in their work, facilitating chemical engineering outreach to all the chemical engineers, but also the wider society in Europe and throughout the world. I'm a chemical engineer by training, and I grew up in the north of the Netherlands, where I graduated from the University of Groningen. And I joined the University of Twente, where I'm now a full professor in sustainable separation technology. Next to my professorship, I am also program director, separations for circularity at the Institute of Sustainable Process Technology. And I'm very happy to share with you that this is all about doing research with companies and with universities. And while I have spent all my career in academia, it has always been in a close connection with industries. And it's also my vision that we should not do things separately, but we should do things jointly. And as such, I think the EFCE is a great body where our working parties all have industrial members and academic members. And I'm very happy to see that also today in this webinar, there is a very strong industrial connection. And this is an activity that is a joint activity of academia and industry, organization by academia, and a very good participation of speakers from industry. Let me say a little bit more about this webinar series. The EFCE is organizing these sessions since 2020. At that time, we started in the COVID pandemic, but the success from the previous years have made us decide that we continue with the Spotlight Talks in a regular way. Every year we organize these. And next to the in-person meetings, such as the European Conference on Chemical Engineering, the next one will be in 2025 in Lisbon, and also annual working party meetings and other conferences organized by the working parties. This is now a very strong element of our program. And this year we will have in this series, in the coming 2 weeks, we have contributions from the working parties and sections on membrane engineering, education, static electricity, drying, fluid separations, loss prevention, crystallization, process intensification, chemical reaction engineering, food. And today, to kick off the series, we start with thermodynamics and transport properties. So over the next 2 weeks, we have 11 spotlight sessions, and all of them 3 or 4 speakers. And we focus on topics that are presented by leading persons from industry and from academia. So the links to all the other spotlight series you can find in the same page where you would also have found this link. And the EFCE promotes the scientific collaboration and support the work of the chemical engineers in 30 European countries. We represent more than 100,000 chemical engineers. And the working parties and sections of the EFCE, and they cover all major aspects of chemical engineering, as you probably have found from the summing of all the activities we will have in the coming 2 weeks. And they provide a very important forum of technical exchange and networking among chemical engineers in Europe. And I would like to conclude, but before I do so, I would like to thank all the people of all the spotlight sessions that contribute to this series of this year for their hard work and effort. And a special thanks goes to Martina Poo from Toulouse, who did a lot of great work in organizing the whole series. Thank you all for your attention, and I wish the speakers and all the attendees to this webinar a very fruitful and successful event. I will give the word now to Professor Maria-Grazia de Angelis and Dr. Antoon, who are chairing and vice chairing the working party of thermodynamics and transport properties, to start the session. Thank you.
Thank you. Thank you, Professor Schuur. And I'm here just to give a few words, to say a few words about our working party. Today, we are very proud of starting the spring edition of the Spotlight Talks. And I will just show you some of the activities that we organize and promote as a working party on thermodynamics and transport properties. And you can see the on our website, all the activities that we promote. I am the chair, and together with the two vice chairs, Jean-Charles Dentin from the academic side and Antoon Tenkate from the industrial side, and together with our secretary, Susanna Kuitunen, we promote many initiatives. We have 62 members, both from academia and industry. We promote awards such as the Mikkelsen Awards for senior researchers that will be awarded this year. And every 2 years, we also give an Excellence Award to the best PhD thesis in chemical engineering, thermodynamics, and transport phenomena. We publish opinion papers. We organize workshops together with industry. We support and promote conferences, and we of course, also are very much involved in the Spotlight Talks of the EFCE. So one of the most recent opinion papers we published is available open access and was published 2 years ago, and is entitled "A View on the Future of Applied Thermodynamics," and partially inspired also today's Spotlight Talks. Normally, we submit the surveys to industrialists in order to gather their opinions and to gather the needs, to understand the needs of industry and to be able to prepare appropriate answers in terms of models, data, and software. This paper was published on Industrial and Engineering Chemistry Research and is available for free download if you're interested. Last year, we organized a workshop together with other two working parties, CAPE and crystallization, and it was around pharmaceutical applications. And there was a very interesting set of presentations and discussion with participants from the three working parties, and a paper is in preparation related to this initiative. We are also organizing the European Symposium on Applied Thermodynamics. This is going to be held in Edinburgh, so I am the chair of this event. It's going to be in June in Edinburgh. Now submission is closed for the abstracts, but you can still register to attend the conference until the 8th of April 2024. Edinburgh is also hosting the European Conference of Chemical Engineering in 2027, so another good opportunity to come and visit Scotland. Finally, today's event was promoted and was inspired by industrialists who wanted to share their opinions and their points of view about thermodynamics applied to industrial problems. And we have a very good list of speakers. I'm not going to introduce them because they will be introduced by the moderators. Today's moderators and the organizers of the Spotlight Talk are Antoon Tenkate and Christoph Held. And now I will leave the stage to them for continuing this Spotlight Talk webinar.
Yeah, thanks, Grazia. So welcome also from my side. My name is Christoph Held. I'm very proud to say a few words on our first speakers, Dr. Paul Mathias. So he has many years of experience as a chemical engineer. He's expert in applied thermodynamics, on process modeling. He started the career in Aspen project at MIT, which is one of the forerunners to Aspen Plus. Switched then over to air products and chemicals and Aspen technology, and then joined Fluor in 2005, and I think quit quite recently. And now he has funded Paul Mathias Consulting, which is managed by him, and he will give us a presentation about how to develop accurate and reliable simulations of chemical processes. Paul, the screen is yours.
Yes, thank you very much, Christoph. I really appreciate that introduction. As Christoph said, I recently retired from Fluor, although I'm still there as a contract person, but I did start my consulting company, and it's a very big consulting company. It's a consulting company of one, and I don't really intend to expand it to. It's really an opportunity for me to continue to do the work that I love doing, hopefully for a few more years. So this talk actually started at the last PPD conference in Tarragona earlier in the middle of last year when we had this discussion, and I agreed to give this talk, and I do appreciate the organizers for inviting me to give it. My talk is based upon my experience, how to develop accurate and reliable simulations of chemical processes. And I hope that together with the other talks in this session, we'll all get a good view of how thermodynamics is being applied today in industry, and perhaps how it should be better applied in the future. So I look forward to hearing what the other speakers have to say too. As I thought about this talk, let me just get that thing off. I was thinking about what the underpinnings are of effective applied thermodynamics. And here are the 5 that I came up with. Clearly, the most important thing is thermodynamics. And I think if we depart from the laws of thermodynamics, our applications will not be good. So that's necessary and valuable framework, and I hope to emphasize that. Good data are very important. And of course, a lot of what I'll show you today are data that actually came from experiments, but we have some other good talks about emerging prediction of data from, say, quantum methods and other molecular simulations. My view on models is that probably all models are acceptable if they facilitate accurate correlations and also ensure reliable extrapolations. And finally, the area that I've been working on recently is uncertainty analysis. And I really think it's imperative, non-elective, and we should be doing it. Finally, I would like to say that our simulations, our calculations should really provide process insight. I think a lot of the academic approach is, their emphasis is how to develop models based upon, for example, intermolecular forces or quantum mechanics. But I think to do that, to be successful in industry, simulation should also enable process insight. And the way I'm going to do this is through 5 examples, case studies. I'm going to go through each of them, and hopefully all of them will have some of the 5 aspects that I've talked about. So let me start with the Gibbs-Helmholtz equation. I wasn't... I was kind of familiar with the Gibbs-Helmholtz equation, but really didn't know it very well. The time when I first encountered it was about maybe 15, 17 years ago, when the aqueous ammonia process, the chilled ammonia process, was claimed to basically be a disruptive technology. It was going to displace all the other technologies for CO2 capture. And many of the advantages that are claimed for the process, I agree with, but the ones that I doubt are really in red here. One of the things they claimed was there was a really low heat regeneration. It's not, for example, if you put me the old units, 800 BTUs per pound CO2, but 260, which is like a factor of at least 2.5, possibly 3. And I'm also showing here the units that you may be more familiar with. The other one is the process claimed low slip of ammonia, which seems unlikely to me because ammonia has a very high vapor pressure. So anyway, in doing all of this, I actually went back and looked at in more detail the Gibbs-Helmholtz equation. And I recently published a paper on it, well, at least recent 6-8 years ago. That one, I listed the useful forms. The first one and the last one are certainly something we use a lot today. For example, we develop correlations by using activity coefficient models together with the heat of mixing. And I recently did some work on the low alcohols. And this, of course, is very traditional. It's in all the textbooks and so on. The other one is the Van Hoff equation. And as you may know, Van Hoff got the first Nobel Prize in chemistry, and I believe it was 1901, so at least 120 years ago. So those two equations are very familiar to us. The one that's not quite so familiar, perhaps, is the relationship between the heat of solution and various properties. The first part of this equation has really been in the literature for a long time, although I don't think it was ever rigorously derived. In 2012, I believe it was, John O'Connell and I came up with what I think is the first rigorous derivation of this. And it turns out that this term, the first term, is really the dominant term, and this term usually can be neglected, but it's good to have a rigorous equation. Anyway, we went on to apply this, for example, to ammonia, water, CO2 data, and I won't go into a lot of details here as to how the model was developed. You probably know, but the key is to get a fundamental model and then simultaneously fit data. The point that I wish to make, though, that's very important, is that we really need to pay attention to the speciation, and that is what species will actually be formed in solution. These typically are ionic species like the ammonium ion and the carbamate and so on. And on the next slide, I'm actually showing you these. We can go into the detail later, but these sort of have the usual equations. Water will dissociate, CO2 will form the bicarbonate as well as the carbonate. Ammonia will form ammonium ion, and this is the formation of the ammonium carbamate. And finally, we may or may not have solid precipitation. With this kind of a model and with this kind of a chemistry framework, and the thermodynamic model, in this case, we've used the electrolyte and RTL model, one can fit data. And of course, this has been done for quite a few years. This is a chart of the CO2 partial pressure at various temperatures against its own loading. And as you may expect, the CO2 partial pressure rises as the CO2 concentration in the solution increases. The opposite is true for ammonia, because as it associates with CO2, its own partial pressure would decrease. And all of this is really in the models. The other thing we did way back was we actually applied the slightly simplified version of the Gibbs-Helmholtz equation and came up with a heat of solution. And there was this paper that came out of Halvard Svensson's group in Norway, as well as various co-authors. And in fact, they said that the prediction came out right in the middle, which is actually what one would expect, because this has been done for a long time and so on. But my point of all of this, though, is that it does work. Now, why did the others come up with a different heat of solution? Well, because they sort of cherry-picked or hand-picked the reaction that they thought was important. And it's not, because, we can't really pick it. The thermodynamics will come to equilibrium. There are speciation data out there and so on. So you can't really pick it. And sort of this is one way, I think, in which we possibly have the tendency to depart from rigorous thermodynamics, much to our peril. So again, my summary of all of this is, and I'm probably preaching to the choir here, is that rigorous models are essential to process design. Models should have the correct speciation. The data is really essential, VLE as well as calorimetric. And then the process simulation does indeed provide a useful tool. The one thing I can talk about in perhaps the discussion later is we're starting to take a deeper look into the Gibbs-Helmholtz consistency. And so, for example, it's very important that the enthalpy of vaporization for pure components be consistent with the vapor pressure, because otherwise you can't really do very subtle analyses. And the other one is that one can measure the heat of solution in various ways, the Gibbs-Helmholtz, for example, as well as through the equivalent of a flat flash calculation, which would be the equivalent. And what we're finding is that simulators such as Aspen Plus, in fact, do not meet that limit. And we are working with Aspen, and maybe we'll publish some more on this area, because that kind of consistency is very, very important in case we won't need to do or want to do a simultaneous data progression, and also want to do calculations like exergy calculations, lost work analysis, and so on. So this is very important, and I think we have paid insufficient attention to it. The simulator that I use is Aspen Plus, but you may use any others, and I'm not claiming that you should have any preference for a simulator, but I believe that all simulators should be analyzed in ways that perhaps we have not analyzed them sufficiently till now. Let me move on now to do uncertainty analysis. Some of you may have seen that I've done some work with the sort of a simple Margulis equation. I'm not going to talk about that today, but what I wish to talk about is some work that I did with my colleague, John Gilmartin, that we have published on uncertainty analysis for CO2 capture. So there is just a lot of information here, but I think I'll share slides with anybody who wants them. But I think the real thing is that process modeling is pretty good. I mean, it works, and all of us, especially in industry, use it on at least a daily basis. But the real thing is, the questions we're not asking are, where are the models weak? How large should the safety factors be? How accurate should the data and correlations be? And can we quantify that? And there are many ways to do it, of course. And I'm not claiming that there is one particular way, but I think what we all really need to do is do uncertainty analysis. So I'm going to show you a particular case study here where we looked at AMP as the particular solvent, as maybe a case we could all look at. But again, I'm just claiming that this is something that we should consider doing as opposed to any particular methodology. I have a methodology, but there may be any others. But the key thing is that we all do this sort of thing. Here is this AMP. It's so-called hindered amine. And here I'm showing again the chemistry model. I'll show this to you on the next slide. But the reason why it's hindered is there are methyl groups that are sort of blocking the amine group. And therefore, this compound, although it's a primary amine and should be able to form the AMP carbamate, it doesn't because of steric hindrance. And therefore, the dominant reaction is to form the bicarbonate. And as I'll show in the next slide, this is possibly an advantage. In fact, this has been claimed by others. So again, here is a comparison between AMP on the left here. You can see the two methyl groups that are hindering the amine group, and the common solvent that everybody shows, which is MEA, monoethanol amine. So you see it's the same thing. So let's kind of look at them. Both are primary. For AMP, the carbamate forms, but it's really minor. And this, in the MEA, it dominates. The maximum CO2 loading for AMP, potentially 1-to-1, if the bicarbonate forms and not the carbamate, whereas in MEA, it's really very hard to go beyond 0.5 because the carbamate does dominate. In terms of kinetics, AMP, it's not clear because it's very complicated to do, but I don't think it's that fast. But MEA is certainly very fast. In terms of the heat of solution, they're sort of equivalent, although AMP may be slightly lower than MEA. Okay. The one thing that I always do, and I hope others do too, is whenever I'm looking at particular solvents, I always try to look at some other solvent and ask whether the broad behavior agrees with what I'm expecting. If it agrees, okay, that reinforces it. If it doesn't, then I've got to question either my own understanding or perhaps the data. In this particular case, I think the broad data does indeed reinforce our understanding. So if we look at the 40-degree isotherms here, and we're plotting partial pressure against loading, if you look at low loadings, MEA is much, much lower by more than order of magnitude, almost 2 orders of magnitude than AMP. And that's emphasize that it's a stronger solvent. Now, I just showed you that because AMP is hindered, you'd expect the bicarbonate to continue to form at high loadings. And indeed, you do get some sort of a cross at about a loading of 0.5. So it sort of, it works. But the one thing though that I should point out to you, and I'm not really going to do this in much detail here, is that as far as CO2 capture goes, though, in the region where you really want to get the absorption, MEA is far better solvent than AMP. But of course, there are other considerations, and I can respond to this in the Q&A, but that's, of course, not the entire story. But again, I think charts like this are indeed very useful. Let me get rid of them. Okay. Sorry, it wasn't advancing. Now we get to sort of perturbation studies. And one of the things that you try to do when you do perturbation studies, so what can I vary? At least that's what I do. So it turns out in this case, one could vary the Gibbs energy of formation of AMP. And just by empirical manipulation, we came to the conclusion that if we vary it by about 1 kilojoules per mole, the VLE changes by about 40%, and if you look at the data here, it looks like the model is agreeing to the data within about 40%. So that's sort of a good perturbation. And then one can, what is that? I don't know why my pointer is not, come on. Okay. Sorry, my pointer keeps getting... Okay. The other thing that I would like to point out, though, is it's very, very important, like I talked about in the first slide, that models meet the right limiting condition. Okay. And in this case, when we apply kinetics, we've got to make sure that at very high residence times, for example, or big reactors, or big absorbers, it does meet the equilibrium limit. And I'm showing here the first model that is actually provided by AspenTech does not meet it. Whereas if you are careful about the way you formulate your kinetic models, in fact, you've got to have a term in there that goes to 0 at equilibrium, it will indeed meet the limit. So here is the CO2 absorbed. The blue line is this model here, and this is the same data but showing for each of the species. In fact, you can kind of see that the carbamate sort of peaks at intermediate to residence times, but eventually drops down. So there's a lot of insight that can be gained from calculations like this. Sorry, but I don't know what my pointer's doing something very funny here. Let me just get rid of that. Okay, so anyway, so that was that. And then one can go in and look at data. Here's pilot plant data. The points here are parity line. And this shows a perturbation of a factor of 10 actually in the kinetics. So that gives us some idea of how we could vary the kinetics too. And then all of this has been published, so I can show it to you, but I want to go through this quickly because I have a couple of other examples. And one can put it into a simulation of a process. And start then to vary various things, like can we vary CO2 solubility, kinetics, mass transfer, interfacial tension. And one can then get a sense of how properties that are needed for design vary as we make these sort of perturbations. Here is one chart that I can show you, and that is there are two things that we looked at. One is that are important. One is the solvent circulation rate, and the other one is the heat rate. So you see, as you slow down the kinetics, in this case, sorry, this is actually the equilibrium. As you make it a weaker solvent, you actually find that the heat rate will go up, as well as the solvent flow rate goes up. And our paper has several of these cases, but I just want to take you to the end here. So the point is that if one does these kind of sensitivity studies, you get a fairly good idea of, with reasonable perturbations, how much does results matter to design change? So that I think is important, and we've published it. So I think a lot of that should be done. In fact, we do it when we go out and give, for example, guarantees or worry about whether our process is working, or when we evaluate pilot plant data, is this result within our uncertainty or is without it or not? And again, like I say, I've published those results. Let me move on to my third example, which is electrolyte system and aqueous dew points. This is something that was brought to me as Fluor. One of our clients was saying that they were having unexpected corrosion in a heat exchanger above what is called here the water dew point. And in fact, that's sort of an interesting concept, because the water dew point in industry typically means where pure water would condense from the system. And so this is this system here. This is the hydrocarbon phase, and you can see it has a lot of on the left are real components starting off with methane, and then higher pseudo components done in a standard way. The important thing for this one is that there is a 5% water, and there is some sulfur impurities at sulfuric acid SO4 at about 5 ppmW. That should be 2 negatives, and that's sorry, I don't know, I missed that. Sorry about this. I'm just going to stop and start it up again. Okay. For some reason, my cursor keeps getting lost. Anyway, so one of the things that we did is then we did some flash calculations. So if we take the system and we run it at the pressure of interest, which is about like 5 bars, and then, for example, calculate what is the fraction of the water liquid phase, the aqueous phase, as a function of temperature. So if you go down at really low temperatures like 20 C, all the water is mostly condensed, right? So you get about 5–8%. And as you start to increase the temperature, it decreases. That's unreasonable. And at some point, there is a very sharp drop in the aqueous content, which would actually correspond to the water dew point, the pure water dew point. But what happens, though, is that the liquid that remains, it becomes really concentrated sulfuric acid. So you sort of get this shoulder. And if you do the calculation yourself, you'll see that that shoulder could be considerable. For our base case, it's about 60 C. And, you know, as you make the sulfuric acid more or less concentrated, it changes. But the point is that you're going to get sulfuric acid or droplets of sulfuric acid in your system at temperatures much higher than what you think is the aqueous dew point. And from our point of view, it means that more expensive metallurgy needs to be used in those conditions. So I'm running out of time, so I'm going to go forward quickly here. I can share slides with you, but here is sort of the simple case, right? So you see there is about possibly a 60 degrees C increase in the dew point based upon water dew point. And then we get to our solution, right? The first one is, can we validate our model? And, you know, we've done various things. The model is probably valid. I don't know how big the increase would be, but it's considerable. You know, it's got to be at least 20, 30, 40 degrees Celsius. So then we get to the problem mitigation. The first one is that we actually ensure sufficient temperature margin. And the second one, possibly eliminate the formation of SO4 but that's very hard, you know, because it doesn't take very much. It's hard to eliminate. So again, the simple solution here would be to give it a sufficient margin and be conservative about materials. I can go on. I don't want to spend too much time on this, but one could do it for other cases too. In this case, if you had HCl as well as ammonia, a strong acid and a weak base, excuse me, one gets other variations, all of which can be calculated, including the formation of a solid, sorry about that, of the solid phase. Okay, I'm going to actually eliminate, in the interest of time, I'm going to eliminate the next one. I can talk about it. This one is actually a removal of methanol from oil that's taken out from the sea after you apply methanol to it to resist hydrate formation. So I'm going to skip that one, and I'm going to go to the last one.
While you skip one, just an announcement to all. If you have questions, attendees, please use the Q&A to write your questions. Okay, thanks. Paul.
Okay, good. Okay, so again, with this one, the key result here is that one can come up with a model for methanol distribution coefficient between an oil and water phase. One can add solvents to it. One can add salts to the model and come up with some pretty reasonable results. Okay, we can do the effect of temperature and so on. The main one in terms of the process insight here, and I didn't get time to show it to you, but I can talk about it, is that there is a very big difference between a single stage and a two-stage countercurrent. And we actually do know that from a lot of the applications that we have, right? Processes work much more effectively if they are countercurrent than single stage or co-current. But this is really a concrete example. In fact, when you talk about process insight, I, for example, have learned a fair amount about the way processes operate, just too simple looking at them through a process simulator and making various changes. The last one I want to talk about is CO2 drying. And the reason why this is important is because we're all doing a lot of rate-based distillation today with, which has kinetics and all of that. And I showed you some of that with CO2 capture. But this is a simpler example that I think makes some points. Okay. This is drying of chlorine. This is from chlorine from a chloralkali process, for example. And when it comes out of the chloralkali process, it's about 1 to 2 volume% of chlorine. And the target is to get it down to 1 ppm. So this is really done by using sulfuric acid for drying, because sulfuric acid, especially concentrated sulfuric acid, is a great solvent for water. So this is done with so-called pump arounds. And one reason for the pump around is you can actually maintain a very high concentration in the top region, which is where you want to remove the water down to really, really low levels. Okay, and so again, you can sort of see that here because the feed is about 0.3 GPM. Again, I apologize if those are not the units you use, is gallons per minute, whereas the circulation needs to be about 250. So there's a factor of close to 1,000 there. Okay, and again, this is sort of the same background, is that, simulations work in principle pretty well, but really how accurate are they? And it's very important to have pilot plant data. And here, for example, there was some Russian data from the mid-40s that turned out to be very valuable. One can go in and do properties. Our models typically work. It's not a big deal. Generally, you get a very big heat of solution at heat of mixing, as you may expect, because it's very, very exothermic. But the other one that's important is as you get to very concentrated sulfuric acid, the water partial pressure drops considerably by many orders of magnitude. And that's what makes it great for drying. These are the transport properties, and you can do that pretty well too. We have published this as a paper, so you can read the details. Again, there is pilot plant data. And again, if you look at pilot plant data, sometimes it's complicated to deal with, it's difficult to measure and so on. But what we did though is get pilot plant data, and then the key now gets down to what really is the area. And this is where we realized that we needed to consider some changes, because the important part here is if you consider drying, right? What this is a vapor liquid situation. And in this particular case, most of the resistance to the mass transfer is coming from the vapor phase, because once the water sees the surface, it's gone. So there's really no resistance in the liquid phase. So the vapor phase is then, as I showed you just a couple of slides ago, the diffusion coefficient of water in the gas phase is pretty well known. So really, when you do this, it comes down to the area. And as you may know, the area is calculated by the so-called dry area, or the specific area, multiplied by a factor. And that factor comes out of correlations. So I'm showing here 3 correlations that are used in industry, and they vary by a lot. Okay, and so one might ask, so why do they vary by a lot? And one reason really is the second bullet item on the right. And that is these correlations were developed for viscosities of, densities of maybe 0.7 to 1 gram per cc, 700 to 1,000 kg per meter cube, whereas this one is about 1,800, or twice that. And the other one is that the correlations were developed for viscosities of somewhere around 1 centipoise or less, whereas here the viscosity could be 30 centipoise. So that really is why it matters. And we came in and we fit our own correlation to it. You see the surface area is really quite small. Okay. If you then go ahead and do all of that, we get a pretty good comparison to the data. It's within plus or minus 20%, which is actually not too bad because this data is very difficult to measure. The one other thing that I want to show you is the same chart. This is the same chart, except what I've done here is make the y-axis a log scale. Okay, so you see plus or minus 20%, and the model is reasonably there. So then you might ask, okay, what happens if I do a simpler model? Meaning, typically what chemical engineers do is I'll use a model with efficiencies. Okay, so but then what I do is the same calculation now, where I treat the absorber, one is as a single flash, and secondly as a two-stage absorber. Okay, and in both cases, you see that the predictions are far, far better of the absorption than the data. And so the one takeaway message from here is that if you start to do calculations like this, you really should be using a rate-based calculation because this is a severely rate-limited process. Okay. Second one is what I showed you in the previous slide, and that is we've got to be careful about the various correlations that come in, because all of them are very easy to apply these days because they come out of the simulator. So you just pick a button. I'm going to use that correlation, except they all may be bad. Okay. The other thing is that once you use this model, we were able to estimate tar height, for example. And here are factors where you change the area from the model, you believe. And so typically we use an interfacial area factor of 0.8, which is like a 20%. And then we came up with the design that's, okay, that column needs to be about 13 meters tall, and it probably work. So that's sort of the engineering result. The insight result that I'm going to give you is in the next slide. And that is, here is the profiles in the absorber, right? I told you that there are 3 pump rounds. So there are 3 levels of sulfuric acid, very concentrated at the top, a little bit concentrated, and then lower concentration at the bottom, about 50% that goes on. So, and there actually is a little bit of a drop here. You can't quite see it, but it's almost constant. On the other hand, on the vapor side, there is variation where you actually do get corners when you go from one pump around region to the next. And most of the absorption actually occurs in the top section. Now, there's not a lot of water that's removed, but there is a big drop in its concentration. And the point is that models like this give you really very good insight into the process. And also, if you then also go in and do the uncertainty analysis, you get a pretty good idea of how much can we trust the models. Okay, so again, this is a long way of saying the same thing. So the models kind of work, but we can, with simulation, especially simulation with some sort of uncertainty analysis, get results that we can trust. And this was a paper that was published 3 years ago, together with my colleagues Paul Solos and Quincy Amen. So that then brings me to the end. So I'm going to put up the slide I started with, which are sort of what I call the 5 underpinnings. And I look forward to any questions or comments that you may have. Thank you very much.
Yeah, thanks, Paul. Was an amazing talk and very extremely interesting, and hopefully also for others examples that are very useful to tackle, and maybe to also to compare with own models, and to use these examples as use cases to validate own models. So the first question is, yes, as a remark, just he wants to have the slides, but I think that is already answered. So Paul said like that the slides can be shared, and this record that you see will be shared also by the EFCE. So that will be that we will be available to all. Then there's a question coming from Filippo Bisotti, asking that sometimes, or quite often, industrial data are not disclosed, or it's difficult to get high quality data. So is there a rule, Paul, a rule of thumb to decide if a separation model should be modeled using a rate-based approach or a simple staged method? That is the question.
Well, I'll give you the opinion of my colleague Henry Kister, whom you may know is like one of the biggest world's distillation experts. And his belief is that for relatively simple systems, even ones that are difficult but are simple, for example, propane, propylene separation, which is actually a very difficult one because relative volatility is that close to unit. He suggests actually using the regular stage approach, but using efficiencies to cut back on the number of stages. So, and I think that from my work to them, that works, and you can analyze plant data and it all comes together. But I think there's other cases. So for example, where there's kinetics involved in CO2 capture, or the example that I just showed you, where it's really very inefficient. And that's because nature is inefficient, at least as far as we can tell. And I can't figure out a way to make it better. From that point of view, I think there's no substitute for a rate-based model.
Yes, I agree. I have another question. Paul, what is your opinion on modeling? Especially, you showed many examples on electrolyte solutions. We had a webinar on that as well, but electrolytes are omnipresent in your slides, more or less. And I also see a lot of different solvents. So what's your opinion on, or your wish to researchers? So where is the highest need for research or development? Is it modeling? Is it data? Is it all? So what would you wish?
Well, let me start with my experience, which is, for example, I showed you the CO2 capture, I showed you concentrated sulfuric acid, I showed you ammonia and chlorine and so on. In all of those examples, in my opinion, many of the models we have are quite sufficient. And in fact, if you put in the right speciation, they all work. The one area that I mentioned is this Gibbs-Helmholtz, and I think that there is more depth to it than we are using it for. So, for example, I can share this later, but some of my colleagues and I are going back to Aspen Tech and saying, your model does not actually agree with the Gibbs-Helmholtz equation. And incidentally, I did another test with the OLI model some of you have done, where you calculate it in two different ways, by a flash, the heat of solution, and you calculate it just by taking the simple derivative with Gibbs-Helmholtz. It does work. So I think we need to be testing these models. There is another sort of, if I can depart a little bit more, there's another simple case. If you test the Gibbs-Helmholtz equation for a simple single-phase liquid, ethanol, for example, right? And you're not careful about getting your enthalpy of vaporization consistent with the vapor pressure derivative through the Gibbs-Helmholtz, you don't get the right result. It doesn't agree, which then tells me that you start to do exergy calculations and so on for such a system, where now the entropy is important. You're going to be wrong. So I think there is a lot of those practical aspects to it. I also do think that there's probably some work that needs to be done in electrolytes for very complicated, difficult systems. I don't know. I saw other papers, so they may be there, but I think for the vast majority that I deal with, I really don't think we need better models. We should be using our models better. But again, that is my opinion, and I'm sure there'll be a long discussion perhaps in the evening over beers and so on as to where it goes, but that's my opinion.
Maybe. Yeah. Okay. Yeah. Thanks, Paul. So thank you again for your very great talk. And Antoon, I give the word to you.
Thank you very much. Thanks also, Paul, for indeed splendid presentation. I would like to move on to the next speaker of today. She's from Neste. Her name is Susanna Kuitunen, and she will be talking about applied thermodynamics as part of simulations, supporting activities ranging from research to investment at her company, Neste. Susanna has been for a long time in her career with Neste. She moved up through the ranks, and currently she's a fellow at technology. And I'm very much looking forward to her presentation. Susanna.
Okay, thank you, Anton, very much for the introduction. And indeed, it's a great pleasure for me to give this presentation, and I'm very thrilled that I was invited. And also thank you, Paul, for your presentation. It was extremely interesting. I'm moving a little bit more on a general level, so I think I'm showing only a couple of equations and focusing more on how we are doing this modeling and simulation work in practice at Neste at general level. So I think two essential models are for reaction kinetics, so kind of the heart of the process, and then the models for thermodynamics and physical properties. And the quality of the simulation results heavily depends on the quality of these two models. And because we are applying the simulation results for troubleshooting our processes and design of the new facilities, it's extremely important. And the quality of the models, of course, it depends on how well we can model certain systems like electrolytes and so on. But it also depends on the expertise of the people who are doing the simulation and modeling work. And that we try to kind of emphasize at Neste that we need to have these competencies. And concerning that, we are learning while we are doing, so I'm sharing a couple of learning cases. And then we all, I think, acknowledge that our thermal models are not yet perfect, so we need collaboration to develop models further. So I started this presentation by introducing Neste so that you can understand like the systems with which we are working with. So Neste is Finnish company. Our headquarters is close to the capital, which is Helsinki. And Neste was founded to secure Finland's oil supply in 1948. And in the beginning, we were just refining fossil crude oil for several decades until the group of experts in our company developed technology to refine vegetable oils to produce renewable diesel. And once this technology was developed, we have been investing the production facilities in Finland, Singapore, and Rotterdam, and currently still expanding the production in Rotterdam. And now currently a major effort is to transform our crude oil refinery in Finland to be fully carbon neutral by 2035. And this figure here, you can already see some actions we have been doing and how the carbon dioxide emissions have been decreasing. And in the scale of our country, this is also significant activity because currently this refinery is contributing is the second biggest emitter of carbon dioxide in the industrial scale. And all these investments and improving the current facilities, it has required a lot of modeling and simulation work. And I predict that will also continue in the future years. But I mentioned that we also need reaction kinetics, and for that we need piloting and reactor experiments. And for that we have research facilities in Finland and in Singapore. And in order to produce data, good quality data for the model development, the modeling and simulation experts are participating in planning of the experiments, and together with the researcher who are responsible of the pilot runs, as well as the analytics experts who are analyzing what are the chemical components in the raw materials and the reaction products. And like it says here, that we are expanding our raw material platform and developing new technologies. So what are those raw materials? Well, at the moment we are refining fossil crude oil and these different fats and oils for the diesel and sustainable aviation fuel production. But also we have some new raw materials in mind, and those are listed here on this figure. So in order to develop models for these new raw materials, we need to have analysis on what is there, like on the component level, and how they are reacting in the reactors. And whatever components we are including to the models, we need to have their physical properties and thermodynamic models in place so that we can predict the full-scale process. And how we are aligning these modeling and simulation efforts with the actual investment project. So everything starts with the concept development, and then we have various engineering phases going into more and more into details, and finally purchasing the equipment and assembling them together to the operational facility. And there are various simulation activities, first of all for the concept development, so mostly steady state and maybe some CFD for the details, and then go into the safety system sizing and control philosophy, startup and shutdown, so then mostly dynamic simulations. And when the plant is operational, we start the troubleshooting and optimization activities. And about the modeling, so one would maybe expect that we will not start simulations until we have kind of perfect model for the system. But that's not often the case, because once somebody has the idea that we could build something based on this technology or this idea, they want to have simulation results as soon as possible so that the concept can be validated and further developed. So that causes a pressure to the modeling activities. So at that point, we need to have access to the experimental data. We need to have access to the state-of-the-art models, predictive models, and so on. And also, we need to prioritize what we will do first in terms of the model development. So kind of discuss with the stakeholders what they think that is the most important aspect, and of course at least be able to produce the heat and material balance as soon as possible. And then while the concept is being developed, we are improving and developing the model further, and maybe once in a while the simulations will be carried out with the updated model. Then maybe during the major engineering or building the facility, there is a little bit quiet phase in the model development. But once the facility is up and running, we are getting data, actual data from the process. So then we are able to benchmark the models and see how far they are from the reality. Is there something that we can improve in the models, or is it like good to go, and we might accept some deviation between the models and the reality. And then about some more thinking about the thermopackage development. So we want to make it as simple as possible. That's very clear. But of course, so that it will fulfill the targets, and about the targets we need to discuss with people who know about the chemistry, researchers, analytic experts, also with the business and other stakeholders in the project, so that we understand what are the different aspects that the thermomethod should capture. And even if we are aiming to as simple as possible, typically there are tens or even more than 100 components in the simulation. And concerning the component selection, of course, we are dependent on the analytics for the feeds and the reaction products. We might look at the literature also. And also at this point, we are thinking whether it's a bulk or minority component, and is there some components that we could neglect so that it's not contributing or our targets, or it's kind of not relevant for the overall process behavior. Then thinking about the conditions, temperature and pressure, and also then start thinking like what kind of phases we are expecting, 1 or 2 liquid phases or perhaps some solid phases. And finally, maybe a little bit non-scientific thinking is that whether we already have an existing thermo method and we also need to add their few components. So then it would make sense to expand that existing model. And another thing is that if we are trying to apply some thermo methods that we have not worked so much previously, do we have expertise to parametricize, and is our company having desire to invest in such parametrization and know-how on how to do it? So finally, we are arriving at the thermo package selection. So maybe final thinkings are whether there are electrolytes. Do we have predictive models for the system? Can we find experimental data to parametricize it? And then we might realize that one thermo method is not enough, so we need maybe 1 or 3, and also it's possible that we are not able to use only one software tool, but we need to use more tools and then simulate so that the data flows between the different software tools. And then, of course, the parameter fitting and the required accuracy are some aspects. And well, people are doing this work. So we have models and tools, but people are using them. So it's important that we have enough brain power in our company and also in the projects. So if we have big project, there might be several simulation experts and then a couple of experts who are giving advice and following the work. So there are regular discussions on the progress and the difficulties. And what we also want to emphasize is learning by doing, learning new skills about the thermodynamics, reaction kinetics, and all the things that are associated to it. And we think that that will increase the motivation and workload sharing and also competence development. And what comes to the thermo competencies, of course, knowing the theory or knowing where to find the theory, it's good in once in a while to revise the theoretical aspects and also how to apply it. So what are the models and correlations and what are the limitations, where to find data, and also like assess whether the data is reliable or not, and what are the software tools. And here are some concrete examples on what are the questions that I have received or my colleagues have received. Some are very straightforward development of thermo package or giving some property estimations. But also there are questions like how to ensure in the model development that the model is accurate enough. And of course, these are always difficult questions and requires discussions on what are the targets of the simulation task and what are the really relevant properties that the person should focus. And also another important thing is to be able to explain the simulation results. The audience typically has some hypothesis or assumptions on how the simulation results should look like. And if we are providing simulation results that are not according to their expectations, we need to explain quite thoroughly the results and what are the underlying phenomena that has affected on the results. Also, we plan in troubleshooting of operations, so they might have some problem and they want to know whether changing some condition, pressure or temperature could help, or we participate in planning of experiments. So there we are discussing like that, how the changes should affect on the outcome of the experimental work. And also one relevant discussion topic in the project can be whether the simulation results are conservative or optimistic from the study point of view. For example, if we are estimating the reactor exotherms, if we are underestimating or overestimating them, so they want to know that so that it can be taken into account in the design, or also it can be also development topic for the model. Okay, then about the cases, and Paul already showed set of very nice examples, and more of those case studies can be found from our working party website and also from many textbooks. And I think the case studies, well, first of all, you learn very effectively from those, and the shared cases can save a lot of resources, enhance the safety and prevent losses in our production. So they are very, very valuable. And once I was in a meeting that in which we were discussing about the reduction of air emissions. And in that meeting, somebody presented an idea that what if we just decrease the temperature in the tank below the lowest normal boiling point? So that would kind of solve the case. And I immediately recalled an example of this shared in Kleiber's book. And I was able to stop that discussion right away. So let's not even consider that it's not going to help us at all. So this case study really saved time. So I didn't have to do any simulations to prove that the idea doesn't work. So we were able to focus right from the beginning on the concepts that would actually work. Okay, then first of these case studies. So we had a discussion in the project that whether we could replace gas 1 with gas 2 or 3 as a stripping agent when we want to reduce a component concentration in the fluid. And in that meeting, we were discussing that, okay, for these gases 2 and 3, we could try different mass flow rates. And then a person did these simulations, and the outcome of the simulation was that the significantly different mass flow rates were required for gases 2 and 3 in comparison to gas 1. And when we were looking at those results in more closely, we were able to explain the results solely by the fact that the gases had different molar mass. So when we have the molar flow of the stripping gas on the x-axis, we can see that the efficiency is kind of dependent on the molar flow rate of the gas. And although the industrial stakeholders typically prefer mass over moles, the most of the phenomena can be explained using moles, like shown in this very simplified Raoult's law, where we have mole fraction in the gas phase and the mole fraction in the liquid phase. So please consider moles rather than mass when you are thinking on what is going on in your process or in your experimental work. Okay, then Paul already mentioned a little bit about the ammonium chloride, and indeed this is something relevant when we are hydrotreating something. So I think simulation experts, they are quite kind of familiar with the requirement that they need to define what are the liquid phases or how many liquid phases they are expecting in the system. So whether there is only one liquid phase or two liquid phases, and they need to define that. But on top of that, we need to think about also the solid formation. And of course, this is obvious task when you want to have solid, but sometimes you are not expecting it. And so you need to really consider carefully the components that you have in the system and whether they could form solids or salts. So in this particular example, so hydrotreating, if you have feedstocks that contain either minor amounts of nitrogen and chlorine, and if you are not kind of having there, for example, washing waters that could solubilize the salts, you very easily have these salts in particular at low temperatures. So very minuscule amounts of these components and you will have salt. And if you have small amounts of those components in your feedstocks, then it can take months or even years to get kind of amount of salt that is causing the problems. Okay, then final example is about the mixing rules, and more details you can find about this from our website. So in commercial simulators, there are, for example, these mixing rules available using either mole fractions or mass fractions. And in this example, I have two components, A and B is water and A is some organic molecule. So you can see that here are the molar masses and here are the pure component viscosities. And when we were testing these two mixing rules in our simulation work, we noticed that these mixture viscosities are significantly different. So which one is correct? Of course, we had to measure, and that measurement confirmed that the mass fraction mixing rule is better. So this is now a little bit contradictory to what I just said, that moles are better than mass. But in this particular case, and with these simple mixing rules, the mass-based mixing rule was much better. Okay, then my final slide on this presentation. So indeed, thermodynamic and physical property models, and accurate ones, they are extremely important for our simulations. And simulations in turn we are using for many purposes in our company. So we need to maintain in the company and also in the academy the competencies and develop them further, so that also in the future decades we have people who can do this work. And if we think about the collaboration between industry and academy, of course, concerning the competencies, one form of the collaboration can be in master's degree or doctoral degree projects. But also it's good to have discussion about the needs for the models and the data. And one such example of discussions was held like 1 week ago, where academia was presenting that we think that this model could be very useful for industry. What do you think? And then we were able to give some feedback and ideas. And I think that was excellent discussion and useful for everybody. Then if we think about the industrial software vendor collaboration, then of course usability of the tools is important, maybe some new features there in particular concerning the models. And if we think about how these collaborations take place, of course, here are some platforms that we are participating, so our working party, as well as these different consortiums. And final thing that I want to emphasize is the experimental data. And I put it here in the center because I think we all think it's extremely important. So let's say that the academia wants to compare their new experimental results against the existing data, or they want to develop new predictive methods based on the data. Software vendors want to develop their parameter data banks so that the industry can more easily use their models. And finally, the industry, we are basing our design on the data. So please, if you are measuring data or publishing data, follow these UPAC guidelines that have been prepared so that we could all get maximum benefit on the experimental data. Okay, thank you, and looking forward to your comments and questions, and you can also send me email if you like. Okay, thank you.
Thank you, Susanna, for your very inspiring talk, giving an impression of Neste to begin with, but also the thermodynamic world within Neste and the role it plays. There are already a number of questions in the Q&A box. In view of time, I think I will keep some for the discussion later. And in the meantime, also invite everybody to still keep on adding their questions if you have them.
Yep.
So first question, I think, is a very generic and difficult question. So I ask to you. The question asked is that if you look at the implementational model for predicting thermophysical properties, how do you think that you can reach a good trade-off between the accuracy of the models and the computational speed?
Yeah, that's a good question, because computational speed is very important. Kind of, if we want to do like a major sensitivity study on the big flow sheets, or if we want to do dynamic simulation, so the speed is important. And one way to apply very rigorous models that may have a lot of require a lot of computations. One way is to kind of generate pseudo experimental data with those models, and then maybe correlate the data with some more simpler models that with which the computations are lighter, and we can improve the speed.
Okay, thank you. I hope this answers the question from the audience. Otherwise, would like to hear that. Another question that has been asked is whether you could say something about the cost and benefit analysis, or has this ever been done on the modeling work? So basically to say, can modeling work actually earn a significant amount of money for the company?
I think such evaluations are now regularly done for at least in some of the model development projects. So we are estimating, like, if we are investing a certain amount of money on the modeling, how much it will benefit the company. So we are doing that at least partly. But somehow for me, it's hard to imagine how we could build new facilities or design new facilities or improve the existing ones if we wouldn't have any simulation tools and models.
Yeah, so if I understand you correctly, basically it's substantial part of the work package anyways that you have to do for engineering.
Yes.
So maybe difficult to say which part of the modeling is contributed to the success of the project.
Well, I think it's very kind of, it's the relevant part of the basic data for the engineering. So if there are kind of significant flaws in the basic data, so in the model accuracy, of course, it will have huge impact on the investment. And may lead to situations that we are not able to run at the capacity that we want to run, or some other issues in the operation. So I see that the role of the models and simulations very, very critical to our company.
Okay, and then one last, maybe simple or maybe not so simple question. Can you share some software to make thermodynamics Feely and LLE calculations fast and accurate?
Can I share? I don't think so.
No, I guess the question is what is good software?
Okay. I don't want to give such comments on what software tools people should use. I think that's something that each company should kind of evaluate themselves.
Okay.
Yeah.
Maybe the next speaker can say something about that, being a software provider himself. But thank you, Susanna, for your presentations and your answers. Then I would like to give the floor to Christoph.
Yeah, thanks, Antoon. So with this, we can announce the next speaker. And we are very happy that he's here. It's Bjørn Maribo-Mogensen. He's a chemical engineer, background in thermodynamic modeling of electrolyte solutions. And as told by Grazia in the beginning, we have this PhD Excellence Award. So that is a person, Bjørn is a person who won this award. So that's a very well-recognized person, and he's always keen to apply thermodynamics to the various aspects of chemical engineering, process simulations and modeling and so forth. And that's why he's still active in both the worlds, in academia and in industry, because he 8 years ago funded the Hafnium labs in Copenhagen, and they aim at bringing together most recent developments in theory and also to bring it to practical and applied case studies. Bjørn, very happy to have you here, and the floor is yours.
Thank you so much for the kind words, Christoph, and thank you for letting me give this talk. I'll just share my slides here. So today I wanted to give you a bit of a talk on how we do systematic development and benchmarking of electrolyte thermodynamic models for solvent-based CO2 capture and transportation. And so I'm also very grateful to the previous speakers for giving such a nice introduction to the field and also diving a bit into the electrolytes, because we'll be going a bit deeper. So a few words. Hafnium Labs is an SME, a small company. We work together with other SMEs and also together with larger companies to develop better thermodynamic models. We develop software that will provide you with ways of ensuring that your thermodynamic models are correct. And I'll show you some of that tooling in this talk. I'll give you a brief introduction to us. Then I'll talk about the need for thermodynamic modeling in carbon capture and transportation. Then I'll try to give you an overview of the challenges that I see and the current state of art, and dive a bit into how we do the validation of electrolyte thermodynamic models in the QProp software. And also look a bit to the future for what I think are good developments that we should be embracing in electrolyte thermodynamics. So we try to solve one of the hardest challenges in chemical R&D, and that is obtaining reliable physical property data fast. And that actually has two legs. One is data prediction, faster than going to the laboratory and cheaper. And another one is milliseconds when we want to do dynamic simulation or process simulation in general. And our QProp software is setting a gold standard for property modeling and helping to digitalize R&D, enabling the typical faster development, better and safer designs, and broader exploration with digital tools. Now, carbon capture is an area we work in a lot because it's key to the green transition, and it's estimated that 15% of the net zero energy target should come from CCUS. We know there's going to be significant investment in the coming years in carbon capture and the infrastructure. And we also know from the chemical industry that applying digital tools brings about reductions in both CAPEX and OPEX. And so we need digital tools. And the foundation of this is thermodynamics. And the problem with thermodynamics is that it tells us what we can do and what we cannot do. So, for instance, these are phase diagrams of CO2 water with the x-axis being CO2 and vapor pressure in the y-axis. And it tells us that water and carbon dioxide doesn't really want to mix. So we need to add additional solvents in order to capture it. If we've captured it and then stripped it from the mixture, we are going to have another stream that is not pure CO2, unfortunately. And another problem is that due to the operating conditions of CO2 near the critical points, so these are isotherms of the density at 305 and 310 Kelvin as function of the pressure in Pascal, we see that there's a huge impact of small impurities. Now, this is 0.5% oxygen and nitrogen compared to the pure CO2 calculated with the Spahn-Wagner equations of state in red, and the Spong model in blue that accounts for the impurities. We can see that it can have a significant effect on the properties of CO2 at certain conditions, and especially at elevated pressures. So we have to think about how we account for this. Another area where impurities is extremely problematic is in actually the whole CO2 capture process. And I'll try to explain a bit, but to the left here, we have a process simulation set up in the tool called COFE, which is a free process simulation tool supporting the CAPE Open standard. Behind the scenes, we're running our own thermodynamic models, and we've set up a very simplified scheme. So we're not including rate-based columns and so on, because what we are interested in is overall fates of compounds. So trying to add new impurities to the feed and then see where they end up after the absorber, the stripper, and so on. And in this particular case, we were looking at the fate of ammonia and the impact of that. Because what is very interesting is that when you calculate the true aqueous dew point from the pure CO2 stream, which really contains mainly just CO2, so 98.25% in this case, before water cleaning, we can see that the impact of ammonia on the dew line of this was insignificant. But if we look at the pH of the first drop of water when we go above the dew point, we see that it can jump by 0.5 points, even though we in that stream only have 0.1 ppm of ammonia. So it can have a significant effect. And ammonia is just one of those impurities that we have to worry about. Sulfur dioxide or others, organic acids and so on, can all contribute to the pH of that first droplet. And unfortunately, that is, of course, important for corrosion and the material choices that we pick for our transportation. So even though these minuscule impurities, we're used to not ignoring them, we cannot when we think about the material of construction. Another problem that was also alluded to earlier is that if we have common small acid like hydrochloric acid or hydrogen sulfide, we can also form some hygroscopic solids, which may develop and cause problems later because they actually capture the water from the air. And unfortunately, if we start by assuming that the properties of our pipeline should be similar to pure CO2s, sometimes it can lead to really bad outcomes, like in this case, where they actually found that the increased level of impurities led to a knowledge gap between the design phase and to a fracture of the pipe. Thermodynamics is also very wary of applying thermodynamic models and equations of state very close to the critical point, because they may not accurately match the properties, but actually now with the pipeline or the transport properties are very close to the critical temperature of 31 degrees. So we can actually expect some effect from this as well. And the bad news, of course, is that while there's lots of value in developing digital twins, they're really limited by the reliability of your physical properties. And unfortunately, it's a garbage in, garbage out situation. And a lot of the models that have been developed do not really work for green processes or even the carbon capture. And one of the problems is that we have little or no information for green chemicals and mixtures. And a lot of times we have to apply the most advanced models, electrolyte models and algorithms, which are only available in very few tools and to very few people. Furthermore, developing models and fitting parameters is both difficult and time-consuming. And that leads to a situation where we can only really model the carbon capture for limited amine processes under limited conditions in terms of concentrations and so on. In the next part, I'll just talk a bit about why it gets so bad. And one of the areas that academia also needs to focus on, for instance, is the chemistry part of this, that we quickly get into a very complex scenario. So, of course, if you just have water, we have deprotonation of water, but then we add CO2 and suddenly we have carbonic acid, carbonate and bicarbonate ions. We can start adding a solvent like MEA, and we can see why it's one explanation why it can be a good solvent is that it reacts with CO2 and forms this carbamate compound. But MEA is also known to be quite problematic because it can degrade. And one degradation example that is well known is that it forms ammonia. And we just represented this with a reaction of water to an MEA forming ammonia and ethylene glycol. But ethylene glycol is a bit more dubious whether that's correct. But ammonia at least is there and it can disappear, and we have to think about that. That unfortunately also adds the ammonium ions, ammonium carbamate ions. We have to think about a lot of molecules whenever we're dealing with this. And it only gets worse if we try to think about sulfur dioxide and NOx compounds that can then form nitrous acid, sulfurous acid, and sulfuric acid, and so on. All of this becomes a pretty big mess, and a lot of things that you have to keep consistent. And this leads to an issue that's quite essential, is that it's very hard to publish anything within this without ending up with very large tables like this one from Hartono, who is developing a new set of ENRTL parameters for the MP piperacene system for CO2 capture. There's simply a lot of numbers, and it's very easy to get a minus wrong, a comma wrong, and then suddenly your model, even though it's working on your side, after publishing, it actually ends up not giving the same results. So reproduction is an issue in this, and that's something we've learned the hard way. In addition to binary interaction parameters, we need temperature, pressure-dependent correlations of other properties like Henry constants, vapor pressures, reaction equilibrium constants, and a lot of the data in order to then validate that the model is actually right. Some of these parameters we can get from published databases. Others we can start predicting with quantum chemistry and group contribution, but at the end of the day, there's no real substitution to getting all of the data together and fit and validate together with that. So I'm trying to, with this slide, just to give you an idea of what is the necessary minimum level, essentially, of what is needed for being able to do general modeling of amine processes. By the left-hand side is an example of a commercially available package called the MSIM that's able to look at different blends of 6 amines, and then also some specific systems looking at CO2, H2S, and also some non-reactive compounds, and also takes into account some of the kinetic aspects that we talked to before. Whereas the literature is publishing papers which are really like nice, thorough, really goes through all of the available experimental data and publishes parameters. But once you then start to think, okay, but I also want to look at sulfur dioxide, ammonia, or other compounds, then you have to start mix and match parameters from different sources, and there's really no guarantee that this is going pretty well. So what we set out to do with QProf was to have a way to quickly implement and validate new models, and also bring together parameters from different sources, also fit our own parameters directly in this system. We've been developing QProf over the past 6 years with more than 5 million euros invested. We've been developing it both to give good predictions for pure compound and pseudo-pure compounds, but also to provide property packages that can be used for process simulation. And today, what I'm talking mainly about is about how we develop these property packages. We have 3 core QProf tools that can either be used together or standalone. So one is QProf Predict, which predicts molecular physical properties of molecules. What's special here is that we include all of the experimental data and do very rigorous benchmarking across all of the different models to provide recommendations of what would be particularly good model for this molecule. Then we can take some of those predictions in the absence of data, or we can take all of the experimental data and put it into the QProf model, which is used to parameterize, validate, and benchmark thermodynamic models for chemical systems, including ions and reactions. Then we can export those models and use them inside of process simulators through the Cape Open interface. We start always with our QProf workflow, which is a unified approach for getting physical properties right, and also understanding the impact of uncertainties, which I really recognize for Mathias for talking about this. I don't have too much time to dive into it, but uncertainties are also an essential part of our workflow. But we start by getting all of the data into one place, and that includes taking data from many different databases so that we can build a specific project database for the chemical system in question. Next, we add different thermodynamic models and are able to benchmark them and select for the best one for your project, after which they can be exported, or you can do further analysis. One of the reasons why this is not really that accessible today is also that in order to do anything related to electrolytes, you need reliable both physical and chemical equilibrium flash and algorithms. And that's something that's really essential to what we've been building to allow you to deal with both aqueous and multiple liquids, vapors, and solids together. That goes into the next slides, where we will be talking a bit about what are the types of validation properties that you use in the validation for your systems. In order to benchmark models, we have to really look at all of the properties that have experimental data, and potentially also those where we can predict the properties. That includes pure compound properties like vapor pressures, but in many models also density and dielectric constant plays a role for predicting the further properties. Reactions are essential to getting speciation right. Binary properties need to be correct, ternary, and you have to account for the different types of phase behavior that can be in the system, including solid phases. And if all of those things come together, then you can start doing reasonable validation curves like this loading curve here, where you have the amount of CO2 per mole amine. This is now MDA and piperazine together with 42 weight% MDA and 8 weight% piperazine. And then measure the CO2 partial pressure on top of this. So these are often the ones that you see developed for these systems, as it's very hard to get these right without having gotten everything else underneath more or less correct. But as we can see, sometimes we might even be missing our target a bit in terms of certain properties, like in this case, the enthalpy of adsorption of CO2 and 30 weight% MDA is slightly off at lower loadings. And these are just important information also for later when you try to assess the reliability of your design. H2S MDA, that's another example of a loading curve, but if you have experimental data available, this is a good way of resolving that. Underneath it all, there's a chemical model that decides the species that are in the aqueous phase. And sometimes you have experimental data available, like here to the right for the MDA CO2 speciation, but this type of data is very rare. In other cases, publications like to the left might give their own speciation, and we can use it to validate our own, but it's also sometimes here difficult to get exactly the same. Simply because of all of the different parts, moving elements to this, that need to be exactly right to get 100% the same model. Below the speciation comes the equilibrium constant. So that's both the reactions and the value of the equilibrium constants, which are of course important to get right. Oftentimes models just look at the equilibrium constants at the saturated liquid. So this is for water, and that's looking great. And also CO2 is looking quite fine, both for the carbonate bicarbonate species. But actually, if you start looking a bit deeper and including all data, you will see that there is discrepancy when we start including pressure-dependent data, because the underlying model for the equilibrium constant or for the standard states did not include pressure dependent. So that's then some important input either for model development or for the uncertainty estimation. In this last part, I'll just show you an example of a tool that we are using here for the ammonia potassium carbonate system for CO2 capture. You'll see there's plenty of compounds, both ions, but also salts involved here. That we have to take into account, and all of these need proper reactions. So there's validation of the reaction equilibrium constants, and we need a thermodynamic model, in which this case we show the validation with the extended uniquark model. I'll go into a loading curve of ammonia as a solvent together with water. And we see here this loading in all of the experimental data that we have available for this ammonia CO2 water system. It's showing some statistics on how good the fit is. And we are then able to also start adding more types of data sets or more data sets that have been measured and are available in our system. We can start adding things at elevated temperatures, but the essential thing is that whereas in a publication, you might end up showing only, say, a collection of figures, we have all of them available here. And if you add more data, then this data becomes automatically available for validation. Next, we look at crystallization curves, which actually is an important thing whenever you're dealing with the ammonia and CO2 system, because at low temperatures, you start actually seeing precipitation of ammonium carbonate species. And so it's important, this tracing algorithm is, of course, dealing with all of the chemical equilibrium on the liquid side, and then just presenting the coexistence curves, at which point we see precipitation using the model. and which type of salts are then shown to precipitate. Next part, I'll just show you some other freezing curves. Here we only have some data for the potassium carbonate solid, but the model also includes predictions of a couple other solids where we should probably go and find the data and just validate. But at least it looks like it's continuous and reasonable in terms of where they start. A final way where we can use it is to start doing some analysis of what happens under different conditions. I'll just show you some of the loading curves that were calculated for water ammonia. This is then just using the model, so it's independent of the experimental data, but it allows you to at least make a comparison on a fair basis in terms of seeing what would different models be doing. So yeah, we can estimate. We show initially just these total vapor pressures and the enthalpy of adsorption. We can add more temperatures to this utility, and start going into also some of the other properties like the partial pressures, which follow the same conditions that we had before. And then we can look at ammonia goes in the other way, the CO2, similar to what Paul also showed earlier. And we can look a more deeper dive into the speciation, which can be used to explain some of the phenomena that we're seeing. So I only had time to show this for one model here, but we have about 30, 40 models implemented in QProfs already. And so similar validations can be done with, for instance, the electrolyte NRTL. And I mean, that's also what we are developing currently. We wanted to be a predictive electrolyte modeling tool, so we can start extending these nice publications to further systems. We know that getting accurate thermodynamics really requires rigor, and electrolyte modeling takes it to the extreme. So getting all of the data together is a key message, that this is something that you have to do in order to know that you're applying the right thermodynamic model for your process. We do also tuning and improving of parameters for these systems. We include all of the custom data that a customer may have in this. And also we are developing on the forefront of electrolyte models. For instance, in the coming 8 months, together with Georgios Kontogeorgis, Jardong, and Gabriel Silva, we are evaluating the electrolyte CPA actually for these CCS-related systems against models like the electrolyte NRTL, and looking very much forward to see how that performs. Because I do think that while it's true that electrolyte models are often doing a pretty good job, they're very complex to parameterize and extend. So we need better tooling for that. And another issue is that they don't necessarily make good predictions for very tricky cases. Like in this case, a multi-phase system of propanol, octane, water, and sodium chloride, which was actually given where the electrolyte CPA was actually able to predict some of these middle phases and top phases. And we've recently been developing a binding debye-Hückel model together with the DTU, which takes into account ion pairing that should furthermore improve on these systems. So I'm very much confident that we are actually moving forward in terms of electrolyte modeling. We'll be able to handle many more systems. We'll be able to do more predictive work. But it is important to be able to get all of the data together and validate that, because they are so hard to get right. Yeah, with that, thank you for your attention. You can feel free to ask questions. Also, send me an email. I'll be happy to respond.
Okay, Bjørn. So thanks a lot for these many impressions and these very well-chosen examples, and telling us that it really sometimes gives us a headache, and really to think about which of the data is correct, which model to use, what is the best treatment of all these. The systems can be very complex, and I think that's where the field moves, yeah, from basic 2-3 component system now to very complex mixtures. I think that's I appreciate your talk, and yeah, thanks for that. There are several questions. I'm not sure we can answer them all right now. Just there are 2 comments. One again is, can we have the presentation at the end? The answer is yes. This session is recorded, and so that's fine, but you also have Bjørn's email address. And about the cube simulator, I think there was a question that can be also assigned, like, yes, it is a process simulator, but it can also predict properties. So further questions about that software, please directly write an email to Bjørn. I think that's the best way. But there are several other scientific questions. One is very simple. One is where to get the literature data. So do you have access to literature databases, or do you, like each scientist, scan different papers, or how do you do it in Hafnium Labs?
So you do a literature survey. There are some databases that are put together that you can use, but I don't think there's one good electrolyte database. There are several that you have to look towards. Some come with constraints, and then there are some that are, say, a lot of the data, I would say, lives really in the companies.
Yep.
And that's also where we spend quite a bit of time integrating the databases that they have access to in QProps.
Right. Right. Okay. What about deep learning? So far, all the models we see is like physical models. What is your view on that? So will we see in the future some deep learning algorithms also for process simulators, as it is already there for chemical synthesis, so similar to that?
Well, I think the field is definitely evolving, and we've seen some very interesting applications to process synthesis. I would say that in terms of electrolyte, I think that we should probably, for now, let the physics decide, but it might be able to help us predict certain properties, pKa's of new compounds, or vapor pressures and so on, in a way that we couldn't do before. Better predictions of solubilities and so on. That's all possible, but it does require good data sets. And the ones that are publicly available are not necessarily the best ones.
That's also my experience. So there are several data sets where you have to be extremely careful, and there is also not plenty of data sets. Maybe not enough for machine learning. Maybe, I don't know. Okay, then a very specific question: is there pizza models for multi-ion mixtures, like with sodium, potassium, calcium, magnesium, halide solutions? Do you have such models as well, or do you trust these? Yes.
I think in many cases they're better, but it really boils down to the experimental data and validation against that. But they have some flexibility in them that can lead to better regression of the data. There are also cases where that is not happening. So it's with these electrolyte models, you have to benchmark and then see. But we have those available. Also, reactive pizza models, I think, are very interesting. We have, for instance, for CO2, I think DEA and some other amines been looking at those reactive pizza models, which are actually performing quite well. So I think that's interesting, and there's some sort of what can be nice is that they are easily understandable in some ways, to look at them from the salt perspective, fit the salt, and so on.
Yeah. And what is dangerous is that they are not very well to be extrapolated. So you that can give you a headache. Yeah. So you cannot trust it.
If you know what you're doing, you apply them in the right regions, and then they can be very useful.
So yeah, better not to trust it too much in dangerous regions. Exactly. Okay, Bjørn. Thanks for this talk. Thanks for the discussions. Thanks for all your answers. And I give the word back to Antoon.
Thank you very much, Christoph. And thank you very much, Bjørn, for your exciting talk, which brings us now to the last presentation. And I guess we take a little bit different corner, actually. Giuliana Giunta, she's a senior scientist at BASF, a senior specialist in digitalization, and working on creating breakthroughs using nanoscale models to the development of soft materials. Giuliana, may I ask you to take the screen?
Sure, thank you. So I will share my screen. Can you see my screen?
Yes, we can see that.
Okay, perfect. Thank you very much for the introduction, and thank you to all the other speakers for the interesting talks. So I'm Giuliana, and as Antoon just said, I'm a senior specialist digitalization at BASF. I joined BASF in October 2022, so it's almost 2 years. So I'm a chemical engineer, and I obtained my PhD in Manchester in materials for demanding environment. Then I've been research associate in Manchester, and after that I moved to the Netherlands for a postdoc in the Dubai Institute for Nanomaterial Science. So before I start, thanks to the organizer for giving me the opportunity to give this presentation. And I also would like to thank my colleagues from BASF for their contribution to this presentation, Anna Laura Del Regno, Stefan Köhler, and Edward Schreiner. So today we will see how we can use applied thermodynamics in advancing liquid formulation. So to see how we can discover and optimize these liquid formulations using molecular modeling in particular. So in this presentation, I will first give you an introduction on BASF, the research that we do in BASF, and the digital approach that we use to research and development. Then we will move to molecular modeling. So I will show you which molecular modeling technique we use to address our problems. And at the end, I will show you how we use applied thermodynamics in 3 specific application cases: laundry detergent, agroformulation, and lubricant for automotive, so viscosity index improvers. So BASF has got its main site in Ludwigshafen. It was born in 1865 in Mannheim, and then it started to expand to the other side of the river. As you can see, it's a very big company, and only Ludwigshafen, the extension is like 10 square kilometers. There are around 250 production facilities, laboratories, technical centers, factories, and offices. So it's a very big company. And as you can see from this map, it has got sites in many countries, like in 93 countries specifically. So we can see that there are sites in China, there are in US, and of course the main one is in Europe, in Germany, Ludwigshafen, where I'm currently working. And let's say that our global research and development presence is, let's say, very important for the long-term success. So for this reason, there are a lot of scientists, and let's say the research and development part is an important point in BASF. There are numerous R&D sites around the world, and in particular, the largest R&D site is in Germany, Ludwigshafen, and there are also in the United States and in Asia. In particular, in mid-2023, they completed the expansion of the innovation campus in Asia, in Shanghai, that started in 2012. So let's say that the main concept that let's say drives BASF is the Verbund system. What does it mean? That all the facilities, all the logistics are all linked together in a way that we can use the resources in an efficient way. So for example, the waste heat of some plant can be used as energy for another plant. So this is an important concept in BASF. There are around 112,000 employees, which are organized in 11 divisions, which are divided in 6 segments. As you can see here on the right-hand side, the 6 segments are chemicals, which provide like basic chemicals, materials, which provide, for example, precursors for plastics, industrial solutions that, for example, provide additives, surface technologies that provide, for example, product for coating, nutrition and care that provide product, for example, for home care and personal care, and agricultural solutions that provide digital solutions and product for the agricultural sector. There are over 78,000 customers from various sectors and 10,000 employees in R&D. So as you can see from the slide and also from what I just said, and also from the chemistry is used in almost all industry in BASF. And actually, this is also what the logo of BASF says. So we create chemistry. So what is the digital approach that we use in research and development? So it's like a cycle that starts with an application profile. This can be, for example, the need from a customer, or it can be, for example, the tech push from some experienced researcher inside BASF. And this application profile is complemented with some pre-existing knowledge in BASF. They can be external, like patent or literature, or they can be internal from some experience already in BASF. And where we actually work, we work between the design of the experiment, so the modeling and simulation group in which I'm part, where we are between the design of the experiment and the application profile. Then, of course, once the experiment have been tested, the product have been tested, we can develop the product. And this is where then there are the engineers that do the scale up if, of course, everything has been optimized and can be now sent to the market. And what we do when we do in the modeling group. So basically, we want to provide solution to challenges that we have. And how we do that, we, for example, can do structural and mechanistic, for example, clarification, or we can calculate parameters for other modeling groups. And we can also develop specific components for formulation, like performance polymers, emulsifiers, dispersant, or rheology modifiers, so a lot of ingredients. And we also, at the end, of course, we also want to develop the entire formulations. And how we can do that? We do that using different modeling technique at different scales. So we use atomistic simulations in which every atom is simulated and all the interactions are described using bond, electrostatic, or van der Waals potential. We use coarse-grained simulations in which instead of considering single atoms, we group the atom together in a way that we reduce the chemical details, but of course we improve the efficiency of our simulations. And then the interactions here are based on Flory-Huggins theory that I will show you later. And then we use also COSMO-RS. These are more at the quantum level, and it is used for small molecules. What we do, we first set up our model, we validate the model, then we perform the simulations, and we provide the analysis and the result to the experimentalist. So according to the different technique that we can use, which questions we can answer then. So if we use, for example, COSMO-RS, then we can answer a question like what is the solubility of some particular molecule, or what are the affinity between what is the affinity between two different molecules. If we use atomistic simulation, then we can understand the key interaction that are taking place in a formulation. And of course, when we use coarse-grained simulation, because as I said, they are very efficient, then we can screen formulation composition, as I will show you later. And we can also understand performance of the formulations. We can also use theory, because these are very important to understand the general trend that we get, or extrapolate the simulation result. There are also some apps that are used to support mainly the lab operation, and these are very useful tools because they can do simple tasks. For example, they can give you information about some chemistry based on some criteria, or like foam stability. And as I said at the beginning, now I would like to show you like 3 different application cases in which we use molecular modeling. The first one is for laundry detergent. It's mainly the topic in which I'm currently working. And when we talk about laundry detergent, of course, we talk about water-based formulations. And one important thing is that, of course, we want to optimize this detergent, but we don't want only that they get the clothes clean. We also want some detergent that help in, for example, improving the, like to reduce the energy consumption when we use the machine, or for example, we want to reduce the water waste. So to address this topic, we use coarse-grained simulations. So what we do, we have specific formulations, and of course there are different molecules, and we define different coarse-grained bead of this molecule, and this is based on different functional group that there are in the molecule. Then what we do, we calculate using COSMO-RS. So you see how applied thermodynamics is used in every step, basically in what we do. So we calculate the structure and electron distribution, and we can get information about the sulfatation free energy. This is directly linked to the Flory-Huggins theory, as I said before, and we can calculate the interaction between the different beads. Then we perform the simulations and we obtain feedback from the experiment. If, for example, the simulation cannot provide the result that we want, we need to go back in the loop and try to improve our model. If instead the simulation is providing us, has been validated with experiment, then we can simulate the full detergent system. And here I just would like to mention this paper. This is a review on multi-scale material modeling in the industrial environment. So I think this could be also an interesting paper of review. So here I would like to show you like an example of simulation for detergent. So you can see it's a quite big simulation box. This is a particle-based. These are particle-based simulations. So the transparent box represents the water. Then these red particles are represented the dirt. And then we have got, of course, our ingredient that help us to clean the substrate, which in this case is a cotton surface. And of course, there are then surfactant, polymer, as soap. So you see that this is a simulation that is composed of 26 million atoms. So it means that it's a really large system, but we are able to perform simulation using a high performance computer. And of course, we can divide our simulation in different cores. So here I would like to show you an example in which we wanted to understand what was the cleaning effect of a specific polymer. So we start with a simulation in which we have got the cotton substrate. The dirt is on top of that because we want to remove the dirt from there. And then we have got our formulation. So while this is the simulation box, just to show you how it looks like. And at some point you will see that during the simulation, all the ingredients inside the box are helping on cleaning the substrate. So you can see that the dirt is forming this aggregate with the other ingredient, and they are moving far away from the substrate. And at some point we will end up with a simulation like that. So we run the simulation for enough time that we can capture some effect. And what we do, for example, in this case, we want to see what is the best polymer composition. So what are the monomers that we need to put, we need to combine to obtain a polymer that has got a good cleaning effect. So there are polymers that do not work very well, and like different composition of monomer that give us polymer that work better. So the second case study that I would like to show you is for agroformulation. So here we want to design polymers that can help in the development of product for agroformulation. And one important thing is that so far we have seen water-based formulation. Now we move to oil-based formulation. And what is the main goal? We want to have a formulation that has got high load and is oil-based. There are the active that of course have got an important function when they are used then by the farmer. And why we want this high load? Because of course we want to cut the cost of transportation. So this is the reason why this high load that is required. And of course, if you think about all the ingredients that we can have inside a formulation for agro application, we could end up like we have different monomers, different surfactants, solvent, active. Of course, these monomers can be combined to form polymers, and we could end up with 10,000 polymers. And we could have, by combining all of these ingredients, we could end up with 100 million formulations that, of course, then are a bit complicated to test all of them. I mean, they are very costly to be tested in the lab. So this is where modeling plays an important role, because what we want to do, as I said, we want high loading of, we want to build a polymer that therefore needs to have good interaction with the active. So it has to be actiphilic. It has to have also good interaction with the oil, because it's where everything is. And also it has to have like good interaction with the water, because as we said at the end, the solution is diluted by the farmer that can use it. So by knowing that, we select specific monomers, and then what we do, we use Cosmo calculation, and we try to understand what are the interaction between different monomers. Here are described as M1, M2, M3. And all of these monomers have got different characteristics. So for example, monomer 1 has got good interaction with the active and good interaction with the water, but is interacting poorly with the solvent. Monomer 2 is interacting very well with the solvent, but very badly with the water. And M3, so monomer 3, is interacting very badly with the active and the water. So what we would like to have, we would like to have a combination of this polymer which contains the combination of these monomers for what we just said. By doing that, we obtain around 50 polymers compared to the 10,000 polymers that we had before. Then we do a screening because, as I said, here we are in oil, and we need to see if this polymer, the formulation, is stable in oil. So we try that, and the problem what is now, because it can be possible that it is stable in oil, but we need to see if it can be emulsified. And sometimes the test here fails, so we need to go back and try to recombine the monomers that we use. So once we got this information, then what we do, we end up with 20 formulations instead of the 100 million formulation that we had. We give this information to the experimentalist, they can process them, and of course at the end we obtain a high loading formulation plus a polymer that can be commercialized. So you can see from this slide that from this process that it's true that we did not end up with a winning formulation, but we really did a very good screening, and from 100 million formulation, we end up to 20 formulations that now, of course, can be tested, and this reduces a lot the cost. So the last application case that I would like to show you is for automotive application, in particular for lubricant. So lubricant are, again, oil-based fluid, and they form a layer between two moving surfaces, but of course they are also temperature sensitive. So what we want to do, we want to add some additives in this lubricant, in this solution, that can control in some way the viscosity. Because if you think, for example, if we are in North America and we can reach temperature of -20, of course, if we have got some oil, it can become like wax. But if we need to use the car, of course, the motor can reach temperature of 150 degrees. So we needed to, in some way, control, and we need to be able to use the car in all the conditions. So for this reason, we have got two complementary additives that we can use. The thickener that give the required rheology for the formulation at room temperature and below 0. While the viscosity index improvers minimize the viscosity loss of the formulation at high temperature. So basically, the viscosity index improvers work at high temperature, while the thickener at lower temperature. So here it's better to use atomistic simulations. We use the LAMPS package, and also we use EMC, Enhanced Monte Carlo, is a software that helps us to build, let's say, our simulations. So here you see our molecule, that is our additive that is inside this box. I would like to mention that this is just an example. So you can see that the simulation box is quite small, so there could be a size effect, but it's just as an example. And what we do, we change the temperature, and we see how the additive is in some way changing the property of our lubricant. And at the end, what we do, we select some performance descriptors. I cannot be into much details, and we see which of the additives that has been added. Here we have got mainly dimers and trimers, and we want to see which is the optimal candidate. So the higher the value of this performance descriptor is, the better is the performance. And also we need to see also these two colors. So if we have got red here and blue here, means that is working as a viscosity index improver here, and is working as a thickener at lower temperature. And of course, here we are able to select our candidate. So in conclusion, I hope that I could convince you and I show you that the scientific computational modeling is a very important tool for driven like the product development in a digital, using a digital approach, because we can test hypotheses at the molecular level. We can give like insight into the system to facilitate, let's say, the understanding from individual interaction at the microscopic level, to the complexity of the formulation that we use at the macroscopic level. And of course, as I show you, for example, for the agro formulation, we can do a screening over thousands of components, and these help us to find promising candidates for the experimentalist that can be tested. So with that, I would like to thank you for the attention.
Thank you very much, Giuliana, for your very nice presentation, focusing on how applied thermodynamics can play a role in formulation design. So a different angle till so far. There are a few questions that came up. If I may ask, first question, what you say is it's used as a pre-screening tool, but how much time is involved before you really get to the test in the lab?
So these, I mean, depend on the length of the simulation. I mean, usually like a simulation of, for example, when I show you, sorry, I probably should have shared the screen again. So when, for example, we talk about simulation like this one, even if it's like 26 million atoms, but we perform simulation for like in like a lot of cores, these help us to get the simulation, I don't know, 1 day, 2 days. So of course, then you have got like the way that we build our system is kind of mechanics for using the software that I just mentioned, Nance Monte Carlo. So at the end is a matter of how long the simulation takes. So, so yeah. But usually, of course, it can be, don't know, week or, but for sure it's less than the experimental time, but also the cost is completely different.
Okay, thank you. And an adjacent question is related to, okay, when you reduce from this large domain of possible formulation to 20 in the lab, what is the possibility that an effective formulation is missed?
Sorry, say again, what?
Well, what is the chance? I mean, you try, of course, to minimize your search domain, which is great.
Mm-hmm.
But of course, there's a possibility that you miss an excellent candidate.
Yeah, I mean, the fact is that, as I said, it could be possible, but the fact is that during the screening that we do, and I think that the moment in which we could have the problem that we could fail is when we, for example, we get the stability here in the oil, but then we don't get the emulsification in the water. And then, of course, the fact is that the monomers that we get, these are from already knowledge inside the company. So we know that we are already working with something that, of course, can be used. So everything like depend if the model is robust enough and we are able to, let's say, get the good result and good information in each step, because of course there is always room of improving the model and going back. Then the success is good. So because at the end, for this reason, I said we are not giving just one winning formulation, but we are still giving an amount of formulations that can be used.
Thank you very much. There's another question relating to the simulation that you do on the formulations that you develop. For instance, the agriculture sector, but do they also include how they interact with water in the environment? So more a life cycle kind of approach.
Yeah, I mean, here you need to take into account like how all these monomers are like interacting with the water or with the like other different solvent. Yes, this was the question.
I think so. And
okay.
Otherwise, the person who asked the question.
Yeah, I don't know if it is more related to probably the way we do the cost graining, or but yeah, here of course, yeah, we need to know how interact like the monomers are. Is based on this scheme. Like we want to know we want a polymer that has got specific monomers that have got different characteristics. We want, for example, a monomer that is interacting well with the active because it has to be, the polymer has to be actiphilic. We want a monomer that has to interact well with the oil because, of course, everything is inside this oil formulation. And it has to interact well also with the water because at the end, when it goes to the farmer and in loco is dilute by the farmer and it can be used, so it's sprayed basically this formulation. Of course, you need to make sure that it can be emulsifiable.
Okay. There are some very dedicated questions. Giuliana, I hope that you can, they are in the Q&A, that you can give an answer to those people.
Yeah, sure.
Because,
yeah, sure. Oh, I can also write my email in case, but yes, I will do it. Thank you.
Because in the view of time, first of all, I would bring forward a compliment that one of the attendees brought to you, that he really liked the simulation animation in your cleaning example.
Thank you.
You're welcome. Then I would like to start wrapping up for the session of today. We have 5 minutes left. There are some general questions still which popped up in general in various presentations. This is related to machine learning and data-driven techniques. I think in general, our approach or the approaches that have been offered today are more science-driven than data-driven. Is there anybody of the speakers who would like to say something about that?
Well, at least I can mention that we have not yet at least used these data-driven approaches for thermodynamics or physical properties. So that's the experience from my side.
Yeah, this is Paul Mathias. I haven't done it too, but I recently was trying to do a review of the literature for CO2 capture. And the one thing I found to be promising, now I guess I'm not an expert, is when you have degradation products, which are very complicated and you want to know whether you can capture them. There's a very nice paper that I saw which looked at machine learning to capture that. So it seems to me that as the complexity decreases and we expect our models to run into difficulty, there is more of an opportunity, I think, for machine learning. But the downside that I see, though, is it requires a lot of data. For example, to use degradation understanding, you require data from the particular plant or the pilot plant that then you can use. And it's not clear to me that that is extendable to another plant or another process. But again, I think it's in its infancy. So I encourage people to continue doing it because it's got to improve. Computers are getting better, and understanding of AI is getting better too. So I would like to see more applications in that area.
Okay, thank you.
I think if I can say something, I think there's also quite a lot of work that I think is promising in terms of just bringing up the speed of doing a given prediction. So, for instance, in quantum chemistry, you have coarse graining of the results from, say, DFT calculations into much simpler models that can run in minutes rather than in hours or days. And we've seen some very promising results with respect to prediction of solid heat of formation, for instance, of salts, which can then build into how we do thermodynamic modeling as well and getting better predictions. So I think whenever it's possible to generate a lot of data using computers, we can reliably apply machine learning to speed up at least. And but getting a lot of chemical data together is hard. It's not that it hasn't been done, but the databases are in the thousands of examples rather than in the tens of thousands, millions of examples. So that makes it difficult. Whereas we have pretty good, say, chemistry-based group contribution theories, or the Cosmo theories as well, that have shown quite a lot of promise and success in the industry for property prediction in the past.
Thank you very much.
May I?
Sure.
Yeah. No, that actually also in BASF there is this. I mean, there are already data scientists that of course use machine learning, but there is of course room also in the group to use that. And as also Bjørn was mentioning, the fact of using so machine learning has been used, for example, from quantum to atomistic, like to do a coarse-graining from quantum to atomistic. But like recently, I've been work on a project in which not internally in BASF, but generally, in which we use machine learning to move from quasi-atomistic simulations to, let's say, single interaction site simulation, basically. So for colloidal system, for example, so ligand stabilized nanoparticles. And I think for the coarse-graining part, I think it's really like mainly for building this model, simple model, it's really powerful. Yeah.
Okay, thank you for all your comments. If I may, I also would like to refer to one of the previous spotlight talks that we organized at the Working Party, which actually was on machine learning in the domain of physical and transport properties. Please have a look at the EFCE website where you can see the recording if you're interested. And based on the question, maybe it's also interesting that we review this 2 years later, because that was in the autumn of 2022, this session. So I would like to wrap up this session. First of all, I would like to thank all presenters. I would like to thank the audience for their vivid questions. And I see that Martien is alive. Do you want to say something to close this event, Martien?
Yeah, of course. Yeah, first I want to thank all the participants for the questions and all the speakers. And I hope you enjoy this kind of interaction with scientific people, and maybe see you for the next series. Okay. Thank you.
Thank you. Bye-bye.
Thank you.
Yeah.
Thank you.
Bye-bye.
Bye-bye. Thank you.